Hi everyone, welcome to our Distinguished Speaker Seminar Series. We're a committee of PhD students who are organizing these talks as part of the NSF Institute. Today we are pleased to have Dr. Wang as our distinguished speaker. He's a research staff scientist at IBM Watson Research Center, New York, USA. He received his PhD from Imperial College London, United Kingdom in 2015. His research focuses on the intersection of artificial intelligence, distributed computing, networking, and optimization, with currently emphasizing on quality and efficiency aspects related to distributed data models, which has a broad range of applications, including distributed data analytics, efficient model training and inference, edge-based artificial intelligence, and large language models. He received the IEEE Communication Society Leonard Jim Abram Prize in 2021, IEEE Communication Society Best Young Professional Award in Industry in 2021, IBM Outstanding Technical Achievement Awards in 2019, 2021, 2022, and 2023, and multiple Invention and Achievement Awards from IBM since 2016. Now let's welcome Dr. Wang.
All right. Yeah, thanks for the invitation and the introduction.
Thank you for being here.
Yeah, it's my great pleasure to be here. And I'll be talking about some recent work that we've done related to balancing the quality and efficiency in future AI systems. So just to give a little bit of motivation and also looking at both data and models. So basically, when people talk about machine learning and AI these days, usually like they may brag about like this is the great model that I have and all that. But in reality, when we really want to deploy these kinds of AI solutions in practice, what we found is that data is actually much more important than the models. This is based on a survey done by Gartner recently. So basically, in that survey, 79% of participants were saying that identifying data preparation and generation is the most common strategic task performed by AI teams these days. And 30% view data volume and complexity as one of the most challenging aspects of AI implementation. So on the right here, there is a quote from someone who was at IBM before. So he was saying garbage in and garbage out. So as we know that the AI models are trained on data, and if the data is not good, then obviously the model would not be good at it either. Okay, so now looking at this data space in a little bit more details. So basically, what people have found in some recent kind of predictive study is that if you look at large language models these days, so we get bigger and bigger models, and we will be using more and more data to train those models. And there's a prediction that maybe in about 2 years from now, we will be running out of all the public data that we have in the internet. Right. So as obviously data is very important for model training. So if we don't have enough data, then we cannot further improve the model performance anymore. So the other challenge is that so even if we have the public data, the quality and other characteristics of the data can vary quite a lot depending on where the data comes from. And for this reason, our team has developed something that we call the data prep kit. So filter out bad quality data from public data sets and keep the good quality data that I will be talking about in a bit more details later on. And the other aspect is, so if you look at the energy consumption of these models these days, of course, there has been quite a lot of improvement in improving the inference performance. But in general, if the model size becomes bigger, then you would also incur more cost, especially for training these models. And a lot of this cost would go into the energy part of the expenditure. And of course, you have to buy the hardware as well. And as a result, there are some big companies who have started discussing about setting up or acquiring some nuclear plants to power these data centers for future model training. But on the other hand, if we look at the human brain, then obviously the human brain is much more efficient compared to any kind of a data center that needs to be powered by a large amount of energy. So there's definitely quite a lot of improvement that's possible, or hopefully it will be possible to improve the efficiency of both training and inference of these models. So what we would like to talk about today is, so we've talked a little bit about the data aspect and about the energy aspect. So we would like to see how we can make use of both public and private data for future model training. And there are some common problems related to both types of data. For example, the volume, quality, and nature of the content can vary quite a lot depending on where the data comes from and also how it's being processed. But something to keep in mind also is that, so if we can filter out the bad quality data and only use the good quality data for model training, then it's very likely that we can have a more efficient training process because the bad data usually they would cause some noise in the whole training process. And so the other goal is we would like to select the most appropriate model to use for some generative AI task. And the question we want to ask here is that because there are so many models out there, and even within the same model family, there are usually different sizes of models. The question then is how can we choose which model to use depending on the characteristics of the AI task that you have at hand. So here, the goal that we would target is that, so we want to choose the smallest model possible as long as we meet some kind of service level agreement requirements. And as long as we meet those requirements, we may not need to choose a bigger model. And in this case, efficiency may not reduce the model quality or the quality of the task itself. So something else that's also interesting to notice is that, so as of today, a lot of these model training and inference, they are happening centrally, like they may be located in some data centers and the endpoint inference API would be provided by the cloud. And these data centers are powered by some centralized energy source. So going into the future, I think what we are seeing more and more also is to have at least some portion of this whole AI landscape being distributed and federated. And that means you have different kinds of data sources. Some of them may be batteries or some solar power in addition to these very large power plants. And you would have federated devices on which you could train some models as well, and also run inference locally. And this would also lead to this diverse and distributed AI agents that we may see in the future. So I think what we would foresee is that, so it's not like everything would become fully distributed or federated, but we will more and more see this kind of a hybrid approach where you have both the central locations where you serve the models and train the models, and then you also have these distributed locations where you can train and serve them as well. So why hybrid? One motivation for that is AI regulations, and especially in Europe. So this is a study that we did about a year ago. There's this AI Act that has been passed, and there's some legislation people, they are looking into how to actually implement that into practice. And based on our study looking into the AI Act, we found that there are certain aspects of the regulation where the federated learning would be more beneficial, and there are some other aspects where centralized learning is more beneficial. So this is also like one motivation of having a hybrid approach going into the future. So in this talk, I will cover kind of this kind of a small matrix here. So I'll be talking a little bit about both centralized and federated learning, and also addressing issues related to both data and models. So more specifically, I would start with talking about an automated data processing pipeline that can be applied at a place where the data is stored. And afterwards, we'll discuss some self-adaptive data reweighting method for unbiased model training. And in the end, I will give an introduction of a recent piece of work that we did on how to select the best model that could be used in AI agents with service level guarantees. Okay, so let's start with how to improve the data quality at the source. So as we said before, and also somewhat showing this figure here, so if we train these large models these days, usually a lot of data comes from the internet, and the data can have different formats, like some may be PDF files, some may be HTML web pages, and so on. And usually such data can include a lot of very diverse kinds of information. Maybe there's some very standard text that you don't want the model to overlearn. or maybe there's some bad information or bad language that you want the model to ignore as well. So what we built is this kind of an open source library that can do various types of data processing, including, for example, deduplication, because if some web page is very popular or some article is very popular, it might be kind of copied in different places, and you see that in different places, but you don't want the model to overfit on those articles. And it also includes different ways of document quality evaluation and some kind of filtering transforms and other things. And in the end, we will tokenize the data, and the tokenized data will be used for actual model training. So looking at this as part of a large language model workflow, basically what we usually do in practice, so this is a pipeline that we use for training large language models at IBM. So we have the data acquisition and ingestion, and we save the data in the cross object store. After some standardization, so we usually save them in Parquet files, for example. And then we can apply this data prep kit to filter out the bad data and sometimes to reformat the schema of the data. And after that, we can do the tokenization, and we can use the data for all of these different stages of large language model training, which can include pre-training, fine-tuning, instruction tuning, and in-context learning, like virtual augmented generation, and so on. And also, usually this is done in a loop. So because the models evolve in newer and newer versions over time, and we may get more and more data over time. So basically, we will apply this whole cycle again and again to improve the model over time. So some of the key concepts that we have in that library are as follows. So basically, we have this notion of transform, and from the raw data, you can apply one transform, getting some transform data, and then you can apply another transform, getting some further transform data, and so on. So in the end, you will tokenize the data, and that becomes the training data. In terms of the filtering operation and the data quality measurement, so usually what we do is to compute the data quality metrics first. So basically, we annotate each data sample with some of these quality related metrics and maybe some other metrics like the language. And then afterwards, we can do filtering to create the portion of the data that we want. And you may do this multiple times to create different portions and then use that data for different phases of training. All right, so the other thing is so this kind of processing pipeline, I mean, regardless of whether it's ours or someone else's, so usually it needs to be scalable across a wide range of scales because there are cases where you may want to do this on a laptop if you want to, for example, inspect the data yourself, or maybe in the case of federated learning, if the data is located at a source, which is a device like a laptop or some embedded device, then you want to apply those kind of processing over there as well because you don't want to share the data around. And it goes all the way up to the server and the data center. And most very large models are usually trained in data centers these days. And there are some technologies for parallelization, like we use Spark and Ray in the backend. So this whole processing pipeline has been used for training IBM's large language models. So we have a large language model family called Granite. This is a paper about Granite 3.0. There are newer versions these days, but we may not have a paper for our different versions. But this Granite 3.0 paper just summarizes the main techniques that we use for both the data processing and also the model training. What we found in the performance analysis, looking at common benchmarks, is that so our model with the data processing pipeline and with some other operations can perform better than the models that we had at the time when this Granite 3.0 model was released, which was in last December. So basically, we are performing better compared to other models that have the same size, like we are comparing the 8 billion models in this case. Something else also is, so we recently also released the data set that's called NiceWeb. I don't have a slide on that here, but that's an open recipe of data processing that can be reproduced using the data prep kit. And there are some performance measures there as well, just to see what kind of data processing is helpful to improve the model performance. Okay, so now let's say we have the data. So we have, let's say, a reasonably good data at the source or somewhere where you can store the data. So now we want to use the data for model training, right? So one question is, how can we train from multiple sources or different subsets of data and remove any bias in the data that the different sources have? And why this could be a bias, it's because sometimes in the case of federated learning, maybe some clients participate more often than others. And in the case of centralized learning, sometimes you may have much more data from one domain compared to others. So in both cases, we would like to make the model good for these different sources of data or different domains, so that we don't have the model to be very beneficial for certain populations, let's say, and not beneficial for some other populations. So just to start, so we mainly look at federated learning case here, but I would extend this to the centralized learning a little bit later on as well. So in the case of federated learning, as some of you might know, so we have a local objective at each client n that is defined as an expectation of the loss functions of the local data. So this is Cn is sampled from the local data set Dn. And then we also have a global objective, which is an average of the local objective. It could be a weighted average, but here for simplicity, I just put an unweighted average. So the goal is to find a model parameter to minimize the global objective, but we don't have access to the data globally. And as you see here, so the global objective is an average of all the local objectives, and the local objectives are defined on the data that's being stored locally. So we need to find a way to solve this problem, but without having to share the data around. So the key idea of federated learning is not to share the data around, so that you can preserve the privacy and reduce risk of any kind of unauthorized access to the data as well. So one common algorithm for federated learning is called federated averaging. So in federated averaging, the idea is so all the gradient descent steps are done at the clients where the data is located, because here you can compute the loss functions and their gradients. There's a periodic parameter update exchange between the client and the server. So the client computes its own update and sends it back to the server. The server performs an aggregation, and after that, the server would send the new global model parameter down to the client, based on which the client would do further local gradient descent steps. We are saying it's doing this for I steps here, and then after that, you will send the parameter updates back to the server. So now this is good if the clients are kind of homogeneous, meaning that they can participate for almost the same amount of time. But the challenge that we are looking at in this work is the case where you have imbalanced client participation rates. And why would you have this? It could be because, for example, different people may have different devices. Some devices might be much more powerful than others. And maybe on some devices, they are running a very large job for something else. In both cases, you could have this kind of imbalanced distribution in terms of how often and when the clients can participate in the federated learning process. So in this case, the client one can participate for like very frequently or very often or for most of the time, but then the client three can only participate for some small amount of time. Right, so now the problem with this kind of participation is that because in the federated learning process, the client participations will be aggregated at the server and they contribute to the global model update. And if some client participates less, that means if we don't do anything specific, then the client would have less influence to the final global model. So what we developed in this work that was presented at iClear last year is, so we developed a way to adaptively weight the client's updates based on some online estimates of the optimal weights, but we don't assume that we know the statistics of how often the clients participate beforehand. And this assumption of not knowing statistics is because before you actually run the system, it's sometimes hard to actually predict how often or what's the capability of the system, especially if it's a new further learning job, maybe it's a new model, you use a different amount of data and so on. So the key insight that we have in the algorithm development and analysis is to combine system statistics with optimization. So now let's take a closer look at the federated averaging algorithm. So this is just a reformulation of what we had in the diagram before. So in federated learning, we have local updates and aggregation. But something that's unique that we didn't show in the diagram before is that, so here we assume that we are sampling the client participation from an unknown process. And this process is unknown, uncontrollable, and can be heterogeneous. So that means some clients may have a higher probability of being sampled compared to other clients. And this is just like a theoretical formulation of capturing the client participation in a way that we can design the algorithm and analyze later on. And also we have the aggregation weights here. So this one is like based on the historical participation, we can compute a weight. And if the client participates less often, the idea is that we can put a higher weight on those clients so that we can still optimize the original unbiased objective that we defined earlier. So now before we look at the algorithm, so let's take a look at what happens if we don't do anything with the aggregation weight. So let's say omega n is always equal to 1, and we can have this theorem showing that, so if we assume Bernoulli distribution of client participation, then the actual objective that the algorithm would minimize is defined like this. So this is like before we have this being a simple average of all the local objectives, but here the objective is weighted by the product of the aggregation weight omega n and the participation probability Pn. And basically, if we choose omega n equals to 1 as in the standard federated averaging algorithm, then this would cause an implicit weighting due to partial participation. And that means if some clients participate less, then the model may not work very well for them. So the model may work much better for the other clients. And this is something we want to avoid because, for example, for fairness considerations, some population may tend to have less powerful clients than others, but we don't want the model to perform worse for that population. Right, so now the idea of the algorithm that we will develop is, so basically we want to develop a way to estimate the aggregation weights. And we will start with Bernoulli distributed participation and then generalize to other participation patterns. As we can see from the previous slide, so the objective is weighted by the product of omega n and Pn. So obviously, if we can choose omega n to be equal to 1 over Pn, then we can kind of solve the problem because then theoretically, the objective would be unbiased. In practice, because we don't assume that we know the participation probability beforehand, we can compute the estimated probability just by counting the number of times the client has participated and divided by the total number of times that has passed. And this could give us this kind of an informal goal that we want to achieve. So basically, we want to choose the aggregation weight omega Tn for each client n to be close to 1 divided by the estimated probability. And this can be also seen as the average of intervals of participation because this is like the total number of rounds divided by the number of rounds the client n has participated. So this could be then estimated using the average of intervals between two participation instances. So one challenge we have here, though, is that because this is an online process, so we don't assume that we can look ahead very further into the future. So we can only observe what has happened so far. And in this example here, in some cases, maybe you have a client that's not connected for a very long time. But overall, probably, if you look further, the overall participation probability is not very small. But if we are just at this point, because at this point, we would estimate omega n to be equal to the average of these first two participation intervals, and this could cause a large overestimate of the aggregation weight. If you have a large overestimate of the aggregation weight, you can probably have instability in training. So tell something that's now a little bit unique in our algorithm is that so we define this so-called cutoff interval to avoid this problem. And the idea is that so this is a hyperparameter k. So if we define the cutoff interval to be equal to k, and the client has not participated for k rounds, then we say at this point we assume that the client has participated once, although in reality it hasn't, and this would create a new interval. So basically, this would shorten the interval that we have here, and it split this interval into two different intervals. And this would, because the aggregation weight is estimated as the average of all the intervals, so this would reduce the aggregation weight and avoid the problem of overestimation. But there's a trade-off here that's also interesting, especially from a practical perspective, because here we are estimating the mean of intervals. So basically, there's a trade-off between how many samples you have and how much bias you have. So if you have a small k, then we have more intervals. So we have a smaller variance in the estimation, but we also have a higher bias because many of these intervals are dummy intervals, and those don't exist in reality. And on the other hand, we have a large k, we will have a higher variance, but we have a lower bias. Okay, so now so that algorithm is well, this procedure is basically the algorithm that we developed, so including this cutoff interval. And we can analyze the performance of convergence of this new algorithm where we do the aggregation weight estimation with the cutoff interval k. So what we found is that, so basically the first term and the last two terms, they are the same as what you would get for standard federated averaging. And only the term in the middle is related to the aggregation weight estimation error. And as we can see here, so if omega is equal to 1 over p, that's the theoretical optimal aggregation weight. In that case, this term would go away. But in general, we would have a bound like this, so we can prove that this term satisfies this upper bound, and this upper bound includes two terms. From the proof, we can see that the first term actually relates to the variance of the aggregation weight estimation, and the second term relates to the bias. And this is also confirm the bias variance trade-off that we saw in the previous slide. So basically, if you have a small k, then this variance term would be small, but the bias term would be large because 1 minus Pn is greater than 0 and smaller than 1. And then we can also get a final convergence rate. So here we plug in some specific choice of the cutoff interval k and also some specific learning rates. And with these replacements, we can get this result. And in this result, the first two terms are standard in federated averaging and also the last term. The term in the middle here is related to the fact that we are doing aggregation rate estimation in an online manner. So what's interesting now is that so as long as you have stochastic gradient that's denoted by the variance of stochastic gradient is denoted by sigma here, or you have heterogeneous data distribution across different clients, the heterogeneous data distribution parameter is defined by delta here. So in either of these two cases, you would have these two terms being dominating because this has a square root of t in the denominator, and all these two, they have a t in the denominator. So this means that although we have to do this aggregation weight estimation, we don't really make the performance or the convergence bound much worse because these two terms remain dominating and they exist in standard federated averaging as well. Of course, if you don't have stochastic gradient, and you don't have heterogeneity either, then we can compare these two terms. But the only difference here is that it has a logarithmic term in the numerator. So this again does not make the rate of convergence much worse compared to the original federated averaging result that you have. Okay, so looking at the experiments, so we consider these three different types of participations in our experiments. The Bernoulli distribution is what we considered. I think someone, Pranay, you have a question?
Yeah, hi Shiqiang.
Hey.
So in your algorithm, is the server deciding what should be the weights assigned to different clients? These
Uh,
omegas?
Yeah, either way is fine. So we assume that the clients make the decision because it's much more natural for the clients to capture how often it has participated. But of course, like if you are considering some cases where some clients may not be reliable or trusted, then probably you can use the server logs as the way to estimate as well.
Yeah, so like suppose a client appears very often, then
Mhm.
you would want to assign it a smaller weight, but it can account for this thing, and in the updates it sends, it can like boost its updates correspondingly, just so that whatever weight you assign to it, like it
Mhm.
doesn't lead to that effect. So like any thoughts of how
Yeah,
to?
that's possible. Yeah, I think there are definitely like trustworthiness considerations that could be considered here, which we didn't consider in this algorithm. Um, yeah, I mean, I think if I don't know, maybe you can measure the norm of the gradient or something like how big the update is compared to other clients. If someone is always giving a very big update, then maybe that indicates something wrong. Or you could probably have some other mechanisms. I think the other way is to, instead of using a small weight for those clients, you can also ask those clients to participate less, because if their contributions are mostly being wasted by applying a small weight, then they don't have to participate so often. So that's also one possible extension, which we haven't considered so far, but that could be an interesting extension as well.
Thanks.
Yeah. Okay, so yeah, so we consider these three different participation patterns. So one is the Bernoulli participation that we consider in the theory, and we also consider Markovian participation and cyclic participation. These two might be more realistic in practice because usually when a client participates, it may participate for a while and then it may get disconnected and doesn't participate any further. So and we compare our algorithm, which is called FedAU, with some of these baselines. And there are two groups of baselines here. So the first two baselines is where we don't need extra information or resources to run these baselines. And the second group is where you need either more memory or you need the known participation statistics. That's basically the actual participation probability in the case of Bernoulli distribution. So what's interesting is, I mean, I think it's kind of expected that we perform the best within the first group. And with cutoff interval k equals to 50, we get generally better performance compared to k going to infinity. In this case, it's basically saying you don't really use the cutoff interval. But it's also interesting that we can actually perform better than those baselines in the second group as well. And the reason we think is because, so for Fed, VARP, and MIFA, they usually, they keep the historical updates of clients and apply them in the next round as a way of variance reduction. But if the client does not participate very often, then some of these updates may be outdated. And in practice, they may not give a good advantage for the progression of training. So that's why I think so that's why we are doing better than these two approaches. But it's even more interesting that we can actually also outperform the case where the participation statistics is known. And we think the reason of this is because so our algorithm adapts the aggregation weights according to the actual sample path that you see in the history of participation. So this ideal theoretical case where you choose omega equals to 1 over p is where, so we consider this overestimation of all the possible participation paths and you basically make the choice based on the average. So I think what this shows is that because we are actually capturing the instance of historical participations, that's why we are doing better than the theoretical optimal choice where you basically look at the average. At least that's our explanation about this for now. And the other thing is, so looking at the impact of cutoff interval k, so if k is big, then we can see that especially in the case where we don't have a lower bound of the participation probability, we can actually get a very bad performance if we don't apply the cutoff interval. And this is also expected because especially when some clients don't participate often, if you just take the average of their participation, the average might be very big, and that can cause some instability in training. So now this approach could also be extended beyond federated learning, for example, to cases where you have different domains and you may have different amount of data from these domains. And as long as you either know the total amount of data or you may learn about the distribution over time, because in some of the training pipelines, the data may come in a streaming manner. So you may not always want to know how much you have in total. And in this case, you can apply the same algorithm as well. But the other case that we also see in practice is where we don't actually have this so-called site information about clients or domains, because in the previous algorithm, we assume that there's a notion of client, so we know how often the client contributes, or there's a notion of domain, you may know how much data you're getting from each domain. But what we don't have this information. So in this case, in the recent work that we presented at iClear this year, we are basically looking at the loss function value itself, and we say that if the loss of the sample is small, then that means the model already knows about this sample quite well, and in this case, we can apply a smaller weight on the sample because we don't want the model to overfit on the sample. And on the other hand, if the loss is big, we apply a bigger weight because we want the model to learn more about this sample. Applying this for pre-training a 7 billion parameter large language model with 175 billion tokens, this actually is quite resource intensive, especially compared to most of the academic research, but this was run at IBM's cluster. So we can see an improvement with about 1%, a bit more than 1% in the both language understanding and reasoning benchmarks and the question and answering benchmarks. So this is a way that we can apply to debias the data contribution if you don't have this site information about clients or domains. So now let me just spend the rest of the time on the last topic. So now let's assume we have the models trained and there are so many models these days. Which model should I use if I have a specific AI use case? For example, the model might be used in some agentic workflows and so on. And especially looking at, for example, Hugging Face, I think this screenshot was taken probably a few months ago. Now there must be more models than this, but even a few months ago, there were like more than 150,000 models. Someone has to select which model you want to use for your use case. And this is still an ongoing work. It was presented at one of the newest workshops last year. So the objective of this work is, so we want to ask this question. So can we select appropriate models from a zoo of models, like you have many models, to minimize the energy consumption while satisfying service level agreements? And what are service level agreements? So basically, in practical applications of these models or any kind of AI technologies, if you are signing a contract with a client, let's say, the client may say that I want your model to automate my process by a certain percentage. For example, in a call center, maybe the model can respond successfully to 50% of the user requests, and the other 50% could be routed to a human. So that's like a service level agreement of a satisfaction of 50%. So now once we have this service level agreement, so we denote this by alpha here. we can formulate this kind of an optimization problem. The objective is to minimize the energy consumption and assume we have capital M models, and this Y is a binary variable saying whether I'm choosing this model small m, and only one of the models can be chosen at any time. So we want to minimize the energy consumption while satisfying the service level agreement in the long term. So T could be quite large in this case. So there are some challenges here to solve this problem directly because the objectives and constraints, they're correlated over time, obviously. So if I choose a big model now, then maybe my overall energy consumption would go up. So maybe later on I should choose a smaller model. But if I choose a smaller model at some point, probably the service level agreement is not satisfied for that particular instance T, but I want it to be satisfied when looking at the overall average. That means maybe sometime later I should choose a bigger model. And also we don't assume that the future request can be predicted because usually it's not possible to predict what, let's say, a new customer would request. So the key idea here is to use techniques from stochastic optimization, or sometimes, especially in the networking community, it's called Lyapunov optimization. We use a virtual queue to capture the aggregated constraint violation. The constraint here is saying whether the time average satisfaction is close to or is greater than or equal to the SLA requirement. And we would like to have a bounded virtual queue length. And basically, because if you look at this expression here, so the queue length itself is the sum of this quantity over time. And this quantity is exactly the constraint about SLA that we had in the problem formulation. So basically, if the queue is bounded, then if t goes to infinity, if you divide the queue length by t, then we can say that the constraint violation is very small, or it goes to 0 as t goes to infinity if the queue length is bounded. So now to solve this problem, we apply a common framework that's called drift plus penalty. So the first part is usually referred to as the drift. So this is the original objective of minimizing the energy. And the second part is actually referred to as the drift. The first part is referred to as the penalty. So that's the actual objective to minimize the energy. The second part is called drift. It's because it's a term that you can get by upper bounding the Lyapunov drift. And this is the queue length times alpha minus this quantity basically that depends on which model you choose and the predicted accuracy of using the model when you choose this model. So the idea here is that now, so if the queue length is big, then this term or this coefficient becomes much larger than the objective itself, and V is a positive constant that serves as a trade-off parameter. So if Q is big, then this coefficient is large, and basically in that case, you want to choose a model for which this predicted accuracy is greater than the SLA requirement. So let's say this SLA is represented as some accuracy of the model as well. So you want this to be greater than this so that this second term is negative. And basically, if the second term is negative, then you can minimize this whole objective. On the other hand, if the queue length is small, then the first term, which is minimizing the energy consumption, that becomes more important. Right? So in this way, it's like, so we can do a trade-off between constraint satisfaction and minimizing the energy consumption. So in the end, the queue length would be bounded and we will satisfy the SLA requirement, but at the same time, we try to minimize the energy as much as possible as well. So we have to predict the accuracy of using different models when making this decision of which model to choose, because we don't actually run the request through all the models. Well, if you have run it through all the models, then you get the result from the biggest model already. You don't have to make the choice anymore. So that's why we need to make the prediction here. And for this prediction, we train a separate lightweight model. We can show that so basically, if we train this model using some online mechanism. So the idea is like with some probability, we send a request to all the models, especially at the beginning. So at the beginning, we may send, for example, 10 requests to all the models so that we can have the separate model trained for predicting the accuracy. But over time, you would reduce this probability of exploration, and you just use the best model that's determined by solving this equation or this objective here. But using this approach, we can show some provable training convergence of the accuracy predictor as well. And by putting this back into this overall formulation, so there's a way to show that, so basically the additional energy consumption due to this exploration will be bounded and would become relatively smaller and smaller if you average that over the total number of time slots, capital T. And also this predictor would become accurate and converge to the optimal solution of the accurate or the predictor as well. So I mean, that was probably quite a little bit of detailed discussion about the algorithm or the insights behind the algorithm, but this is the overall algorithm that we have. So we have an exploration probability, and we explore with this probability PT. And if we don't explore, then we choose the model based on this objective here. And in either case, we update the virtual queue based on the actual accuracy that we obtain from the model. So in this way, basically the virtual queue, because it captures the constraint, so the constraint is related to the actual accuracy, or it could be some other metrics. We are sending that to a binary value, for example, whether it's satisfied or not satisfied. But in this preliminary work, we are using the accuracy of the model. In this case, it's just like this is capturing the actual accuracy you observed, and by showing that this queue length is bounded, we can show that the constraint, the SLA constraint, is satisfied if T is large as well. Okay, so looking at the experiments, so this is actually run on a real test bed that we had at the university, Technical University of Munich in Germany. So basically what we can see here is that our algorithm is called MES Plus, and these are some other model choices and algorithms. For example, so we have two different models here. If you only choose the smallest model, we have a small energy consumption, but the accuracy does not meet the requirement. And if you always choose the biggest model, we can meet the requirement, but the energy consumption is very big. So now if you choose the algorithm, the model randomly with some of these constraints in mind, so we can satisfy the constraint, but the energy consumption is worse than using our algorithm. And the reason is because our algorithm really considers both the constraint satisfaction and the objective function of minimizing energy consumption. And if you do this random with constraint, it's like you just arbitrarily choose according to a probability that does not consider the difference in the energy consumption at a certain time. Okay, so now these are some other experiments about the choice of the control parameter V. And if you're familiar with this kind of stochastic optimization, you'll probably know that. So V controls the trade-off between energy minimization in our case and constraint satisfaction. And if V is large, then basically we would spend less energy, but the accuracy expressed in blue score here would go lower as well. Yeah, so that's all. So I've talked about three topics briefly. So one is how to automate the data processing at the source of the data, and we introduced this data prep kit and said a little bit about how that's being used in large language model training pipelines. And the second one is self-adaptive data reweighting for unbiased model training. We introduced FedAU, the algorithm where we adapt the weight according to client participation history. And we also introduce some extensions, including one that's not requiring any kind of side information. And then we talked about these AI agents with service level guarantees and described this MES plus algorithm and showed some results. Okay, so that's all. Here are some of my collaborators that collaborated on the work that I talked about. All right, any questions?
Thank you very much, Dr. Wang. It was a very great talk and very insightful. Thank you very much. So for the audience, if you have any questions, you can unmute yourself and ask directly, or you can put it in the chat box and we can ask for you. And actually, I have a question that I want to ask. So like it's maybe a follow-up question from the previous question. So do you think your algorithm for the weights for the clients for the federated learning can also solve the problem for fairness concern, like to like handle the bias like for minority clients and things like that?
Yeah, I think it could be possible, but I think for fairness, there are sometimes some specific formulations that you will have to think about. Yeah, but at a high level, I would say that's possible. But depending on what specific fairness formulation you want to consider, we may have to make some adjustments or some extensions to that kind of algorithm.
I see. I see. Thank you. And also regarding the data toolkits that for the pre-processing, so how is like the performance of the data toolkit? Like what's the delay? I'm curious. Like if we can use it like for the cases when we have like the data comes online. So it's like we have the data will add incrementally. So can we
Yeah,
use it?
so usually those well, it depends on what kind of models or algorithms you use for processing, because that toolkit itself is more like a wrapper, so we can implement different transforms. If the transform uses a large language model, for example, then obviously that's not very efficient. But in reality, what we usually do is to apply some small models like linear classifiers or some basic metrics like counting the number of words, for example, and divide that by the sentence length and those kind of things. So those definitely will be very quick. But I think the library for now is not really developed for the case where you have streaming data input. But it could be extended, or I mean, or you can just implement the algorithms directly for quality quantification if you have a streaming data input. Yeah, I mean, for our case, it's like it's so we have all the data stored somewhere, but of course you process them in a streaming way, but it's not like a real-time streaming input.
I see. I see.
Yeah.
Yeah. Okay. Thank you. Thank you very much. So any other questions from?
Yeah, can I ask? So, Shiqiang, thanks for the great talk. Can you like go to the algorithm you had, like I think it was slide 32 or 33, where you had this virtual queue algorithm?
This one?
Yes. So, like when you say this exploration probability, so with this much probability, you are going to like basically look at all the models, right?
Yeah. Yeah.
So this would so like I have one high level question and one specific question. So if you're looking at all the models, then you are essentially like the constraint violation you would incur is at least t to the 2/3 if you are running
Well,
over t.
it's not the constraint violation. Well, as long as we assume that the largest model can always satisfy the request, or at least the ratio that a larger model can satisfy the request is bigger than whatever requirement you have, because otherwise you will never meet the constraint. But because our constraint is on the service level agreement, so it's not on the energy itself. So if you do exploration, you will incur more energy, but it doesn't affect the constraint. You actually make the constraint a bit better, the satisfaction of the constraint a bit better. Yeah, but because this probability decreases over time and is decreasing in the cube order, the cube root order. So that's why, like, if you do an integral of this or sum this up, so basically that would be sublinear. It's not a linear increase. So that's why if you have long enough time, then basically the probability of exploration becomes less and less, and on average that would vanish.
So the general question I had was that like in this online learning setting where you have you try to minimize the loss you try to minimize the regret, and then you also have some constraints. You get this trade-off between what kind of regret, sublinear regret you can achieve and what kind of constraint violations you can achieve. And you get this trade-off between you can't have very optimal, like you can't have optimal regret and optimal constraint violation at the same time, right? Like there is this trade-off. So do you observe the same thing in your case, and like is the trade-off comparable to online learning setting, or is it a different?
So this is slightly different from online learning, because in online learning is where you make the decision first and then you observe the feedback. Right. So in this case, we assume that we know the energy consumption and the accuracy. Well, we make the prediction of the accuracy, but then there's a bound between the predicted accuracy and the actual accuracy. So it's not really an online setting where you don't know anything about the response. So it's slightly different. Yeah, but here, like for energy consumption, we currently assume that it's known beforehand, maybe based on some profiling or whatever. But yeah, that could be relaxed in some future work if you don't know anything about the energy, and everything could be adversarial. Let's say you may get very different outputs and see what's the regret and whether you can still satisfy the constraint or not.
Right.
Yeah.
Okay, thanks. Thanks a lot.
Yeah, thanks. Nice meeting you, by the way.
Yeah, same here.
Yeah.
So if there is no other question, I want to thank Dr. Wang again. Thank you very much. And I will want to pass the floor to Yining for career development question. Thank you.
I guess just before that, I need to stop the recording. Just a sec.
Thank you.